Now we're going to discuss the second major group of instructions in the PDP-11 instruction set, the double operand instructions. Do you remember the format of a single operand instruction? It consists of an opcode indicating what operation is to be performed and a destination field containing information enabling us to find the operand. Do you also remember that the destination field was further divided into two parts, an addressing mode and the general purpose register? The addressing mode specifies how the register is to be used, and the register part of the field specifies which general purpose register to use. With double operand instructions, we essentially add a second operand field to the instruction word. We call this second field the source field. Notice that this source field is also further divided into an addressing mode and the general purpose register, and therefore is identical in format to the destination field. Thus, the double operand format consists of an opcode specifying the operation to be performed, a source field which provides information allowing us to find the first operand, and a destination field allowing us to find the second operand. These source and destination fields are completely independent. In each of the fields, we can use any addressing mode with any general purpose register. Here, for example, the source field uses addressing mode 0 with register R1. Thus, R1 contains the source operand. The destination field, on the other hand, uses addressing mode 2 with register R3. Thus, R3 contains the address of the destination operand. Once the instruction is executed, this address is automatically incremented. Do you remember the function of bit 15 in single operand instructions? We said that when bit 15 is a 0, the instruction operates on a word of data. However, when bit 15 is a 1, then the instruction operates on a byte of data. What about double operand instructions? Well, it's the same thing for double operand instructions. If bit 15 is a 0, it specifies a word operation. If it is a 1, it specifies a byte operation. However, there is one exception. This occurs when using an opcode of 6 with a double operand instruction. In this case, when bit 15 is a 0, it specifies an add operation. On the other hand, when bit 15 is a 1, it indicates that a subtract operation is to be performed. In summation, we might say that when dealing with add and subtract instructions, bit 15 is part of the opcode. An opcode of 06 calls for addition. An opcode of 16 calls for subtraction. Now, let's look at some of the jobs performed by typical double operand instructions. We'll see what makes these double operand instructions so powerful. The move instruction is one of our double operand instructions. It allows us to transfer data from one place to another. For example, we can move the contents of a GPR in the processor into a specific memory location. The GPR is our source operand. The memory location is treated as our destination. Notice that the entire move operation from one place to another is accomplished with a single instruction. Compare is another double operand instruction. The compare instruction compares the two operands and then tells us whether the source is larger, whether the destination is larger, or whether they are both equal. The mnemonic for this compare instruction is CMP. The add and subtract instructions do exactly what they say. The add instruction adds the source operand to the destination operand and stores the sum back into the destination. The subtract instruction subtracts the source operand from the destination and places the difference in the destination. Notice that we're taking two numbers and performing an arithmetic operation, all by means of a single double operand instruction. Did you notice another similarity between these double operand instructions and the single operand instructions? That's right. Except for compare, the result of any instruction is always stored in the destination. In the case of the compare instruction, the result is indicated by setting appropriate condition code bits in the processor status word. Now, let's examine a typical double operand instruction, such as move, a little more closely. Any addressing mode can be used with any GPR for both the source and destination fields. This combination of addressing modes and GPRs allows us to use a move instruction to transfer data between any two Unibus devices. You can see the versatility of this move instruction, where R0 contains the source operand and R1 contains the address of the destination. Here, for example, with one instruction, we can locate data contained in a general purpose register in the CPU and move the data into an I/O register. Or, with the same instruction, we could move data from one memory location to another memory location. Or, we could move data from an I/O device register into the CPU for some type of modification. Or, we could transfer data from an I/O register into memory, and then by means of the auto-increment addressing mode, advance our pointer to the next sequential memory location, and so on, depending on what addressing modes and registers we use for the source and destination fields. All other double operand instructions, such as add, have the same versatility. Here you can see that a number in one memory location is added to the number in a second memory location using just one add instruction. Remember, the results of the addition are always stored in the destination, or in this case, the second memory location. Now that you're somewhat familiar with what these double operand instructions do, let's see how we go about selecting specific instructions to solve a particular problem. The problem is that all current payroll information is stored in memory. Your supervisor just informed you that he wants a hard copy of this data to analyze. Rather than tying yourself in knots trying to figure out how to get this information out of memory and print it on the output printer, perhaps we can use some of our double operand instructions to solve this problem rather easily. Let's start out by looking at our known factors. We know where the payroll data is located because we have the starting address of the data. We also know the size of this block of data. In addition, we have the address of our printer's buffer register. Based on the problem and the information that is available, let's make an analysis at this point. The analysis is quite simple. We want to first get one character from memory and then move that character into the printer. If we should make the memory the source operand, or A, and the printer the destination operand, or B, then you can see that our analysis says get A and move it to B. However, before any characters can be transferred, we must set up the initial conditions. First, we load the starting address of our payroll data into one of the general purpose registers. This starting address, or pointer, tells the CPU where to find the first character of data. We must also tell the CPU how many characters, or 8-bit bytes, are to be transferred to the printer, so we set up a counter. The value loaded into this counter corresponds to the number of characters in the block of payroll data. This completes our initialization steps. The next step is to check the printer to determine if it's ready to receive a character. The CPU will remain in this simple wait loop until our printer signals that it is ready for data. When the ready condition is detected, the CPU can drop out of the wait loop, get one character from memory, and transfer the character to the printer. After the character is moved to the printer, we increment the pointer so that it now contains the address of the next memory location. We must also keep track of how many characters have been transferred. Therefore, we decrement the counter by 1. At this point, we can check the value stored in the counter to determine if we're done. If we're not done, in other words, if the counter is not 0, we want the CPU to branch back to the step labeled ready and transfer another character to the printer. Our processor will remain in this loop until the counter is decremented to 0. A count of 0 indicates that we are done. All of the characters have been transferred to the printer. Therefore, we can now stop the CPU. At this point, let's try writing an actual program to print out a series of characters from memory. These are the known factors. First, the starting address of the data block is 600. Secondly, the number of characters we want to transfer is 76. And finally, the printer address is 777566. The first step in writing this program is to set up or initialize a pointer. We do this by moving the starting address of 600 into register R0. Next, we set up a counter by moving the number of characters to be transferred, in this case 76, into register R1. Our program must now check the printer to make sure it's ready to receive data. When the printer is ready, it raises a ready flag located in its status register. Our program must test this ready flag to know when we can use the printer. The ready flag is bit 7 of the I/O status register. When this bit is set, it indicates that the device is ready for use. We'll cover this status register in more detail later in the course, but for now we simply want to know how to test this ready flag. One way is to use another double operand instruction, the bit test instruction. This instruction performs a logical AND between a known bit and an unknown bit. For example, if we were testing bit 3 for a 0 condition, we could place a known value of 1 in bit 3 of another word. The bit test would logically AND these two bits, and if they were not equal, in this case if the bit under test was 0, the result would be 0. A 0 result would therefore set the Z condition code bit in the PSW. To test the ready flag, we can use this bit test instruction. Notice that we are only testing the low byte of the status register, or CSR. The ready flag is bit 7, or the sign bit of this low byte. We really don't care about the other bits. Therefore, for the known value that we will use as the source, we place a 1 only in bit 7 and zeros in all the other bits, because bit 7 is the only bit we desire to test. As you can see, when the ready flag is set, the logical AND function of the bit test instruction produces a 1, indicating the printer is ready. This result sets the N condition code bit because, in this case, we're testing bit 7, the sign bit. Therefore, when waiting for the ready flag, the flowchart first tests the ready flag, then branches back to test it again if N is not 1. We test the ready flag with a bit B, number 200 status register instruction. We keep testing for ready by branching if N is not 1. Thus, we keep looping around until the ready flag is set, at which time we can proceed with the next instruction. Now we're ready to transfer a character from memory to the printer and increment our pointer. The first part of this instruction, move byte R0 plus, moves the contents of the location specified by pointer R0 and then increments the pointer. Notice that we are using the absolute addressing mode for the destination field of our move byte instruction. Therefore, the second word of this two-word instruction contains the address of the printer that is to receive the data. Because we have just transferred one character, we want to keep track of the number of characters transferred by decrementing the counter. We do this with a decrement R1 instruction. Each time a character is transferred, the count stored in R1 is decremented by 1. Finally, we want to check for done by looking at the counter. If we're not done, that is, if the counter is not 0, we branch back to start and transfer another character. On the other hand, if we are done, the counter is at 0, and we simply execute the next instruction, which is halt. This, then, is our finished program. The initialize portion sets up initial conditions, such as specifying the starting address and number of characters to be printed. The printer ready portion tests the printer ready flag to make sure that the I/O device is available. When the device is ready, the print character portion transfers one character from memory to the printer and keeps count. Finally, the done portion checks the counter to see if we're done. If not done, we do it all again. Otherwise, the program stops, having finished its job. At this point, let's take a short break. When you come back, we'll discuss another job that double operand instructions can perform.